One of the things that you can do is use your knowledge of sine and cosine now to your advantage. We know that a sine wave starts here and goes like this, right? Between 0 and 2 pi. So at 0, pi over 6, pi over 4, pi over 3, 2, or pi over 2, etc., right? But at 0, it's at 0. At 90, it's at 1. At 180, it's at 0. And at 270, it's at negative 1. And at 360, it's back at 0. Okay, so you can use that sine wave to your advantage to be able to easily figure out what those quadrantal angles are. Okay, same thing with cosine. Cosine, we started high and went like so, and that was one full period, one complete cosine wave. So my cosine starts out at 1, and at 90, it's a 0. At 180, it's negative 1, and at 270, it's back at 0, and at 360, it would be high again at 1. Okay? Makes sense to everybody? Now, sine of 30 can get you started. What's the sine of 30? 1/2. Okay? Let me show you a shortcut for this one. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Okay? So shortcuts. Working our way backward, sine and cosine are cofunctions. So 60 and 30 are 90 degrees apart, or they add to 90. They're complementary cofunctions. So we'll get a square root of 3 over 2, square root of 2 over 2, 1/2. Tangents to sine over cosine. 30 has all those 3's. Sine over cosine, sine over cosine. Okay? And sine over cosine. Okay? Now what gets interesting is here. When we take 1 divided by 0, what happens? It's undefined. 0 divided by negative 1, negative 1 divided by 0. Okay, we're going to look at that here in just a moment. Okay? Now we're just using reference angles. 120 degrees is a 30-degree angle in the second quadrant. What's positive in the second quadrant? All students take classes, so sine is positive, right? Okay, everybody else in here is going to be negative. Okay, 120 is a 60-degree angle if we drop it to the x-axis. So it's the square root of 3 over 2. And negative 1/2 for cosine. Okay. And then reverse your tangents. Okay. 210. What kind of angle is that? 30. In which quadrant? Third quadrant. Okay. Who's positive in the third quadrant? Tangent. So we know we're having a positive tangent. Everybody else is negative. And then you write your 30s. Last quadrant, who's positive? Cosine. Everybody else is negative. And what is a 300-degree angle? A 60 reference angle. So we're putting our 60s in here. sine of 60, square root of 3 over 2. Cosine 60, 1/2. Tangent 60, square root of 3. Cosine, or sine of 45, square root of 2 over 2. Same with the cosine, 1 for tangent. Being able to quickly come up with those values can make all the difference in being able to do really well on the ACT or some other standardized test that's timed. Okay? Now, let's graph the tangent of x here. Okay? Let's think about what's happening. When we are at 0, tangent is 0. When we are at 30, we're at the square root of 3 over 3. Someone quick with the calculator, what's the decimal equivalent to the square root of 3 over 3? Okay, at 30 degrees is going to be a pi over 6. So at pi over 6, we want to know how high up the tangent is going to be. What's its value? Okay, so on your calculator, find the tangent of 30 degrees in degrees. So calculator's in degrees. If it's in radian, you've got to find the tangent of pi over 6. And what's the tangent of 30 as a decimal? What was it? 0.57. So at 0, we're at 0. At 30, we're at 0.57. So we're almost halfway up. Okay, we took the tangent of 30 degrees. Okay, and this is the decimal equivalent to, or the fraction's decimal equivalent is 0.57. Okay, so we're almost at 0.6. Okay, 45. Tangent's 1, isn't it? Okay, so up here at 45, I'm at 1. Okay, what about at 60? Tangent of 60 is the square root of 3. What's the decimal equivalent of that? 1.73. So 1.7 is good enough for what we're doing here. So it's almost up here at 2. Okay? And granted, these tick marks are every 22.5 degrees, so I'm a little bit off. But that's okay. Now, what's the tangent of 90? Undefined. Okay? What would be the tangent of 80? Let's see. Tangent of 80 degrees, if you're in degrees. 9, or am I in degrees? Let me check my mode. I'm in radians. 5.6, okay? So do you see that as we get closer and closer to 90, we're getting higher and higher up? What's the tangent of 89 degrees? Tangent 89, 57.2 or 0.3. Tangent of 89.7. 191. Okay, so the closer and closer and closer it gets to this pi over 2, the larger it gets. But it can't be pi over 2. Why not? Because it's undefined there. Okay, so what is this line? Asymptote. Okay, it can get really, really close to it. It's a vertical asymptote, but it can never, ever, ever cross a vertical asymptote because we're dividing by 0. Let's look at what happens on the other side. Okay, if we are at negative 30 degrees, that is our 330 degree measure, right? Okay, so we're going to be where? Negative 0.57. Okay, so it looks like a mirror image, doesn't it? Okay, negative 5.7. Okay? When we're at a negative 60 degrees, or a negative 45 degrees, we're at negative 1. Negative 60 degrees, where are we going to be? Negative 1.7. Okay? So do you see that it's going to be asymptotic to the negative pi over 2 as well? So is this an even or an odd function? Odd, because it is symmetric with respect to? Okay, when you're looking at it and you can see that it's symmetric with respect to the origin, it's doing a John Travolta kind of thing, okay, then it's an odd function. And if it is symmetric with respect to the y-axis, then it's going to be an even function. That makes sense to everybody? So tangent's an odd function, okay? Now what's going to happen over here at pi? Same thing, right? We're going to be at 0, and we're going to go like this, and like this. Can't be 3 pi over 2. Okay? At 2 pi, same idea. What's that? So I would draw those, yep. That way you've got a guide. At negative pi, we're at a 1, or I mean, sorry, a 0, an intercept. Can't be negative 3 pi over 2. And if it helps you to draw those asymptotes as guides, make sure you dash them because they're not part of the graph. Your calculator, if you're not careful, will connect them because it tries to connect the end of one with the beginning of the other. But those asymptotes are not actually a part of the tangent. Everybody got a sketch? All right. So this is the graph of the tangent. We just got done graphing it. What is its period? What does period mean? Anybody remember what the period of the sine was? Pi over 2 when we moved it, right? The period of the sine was 2 pi. Why was it 2 pi? One time it takes to make one full sine wave, right? One full graph, one full cycle. Okay. Cosine is also pi over 2. Sorry, 2 pi. My fault. 2 pi. Okay. So how long does it take to make one full cycle for the tangent? Here's one complete one, right? How far is that on the x-axis? Negative pi over 2 to pi over 2 is how much? Pi. Between pi over 2 and 3 pi over 2, pi. Between 3 pi over 2 and the next increment will be pi. So your period on your tangent is pi. It's a very busy graph. It does a lot more in a lot less time. Okay? What's the domain of the tangent? Yep, it can be between negative pi over 2 and pi over 2, but it can't be negative pi over 2 or pi over 2, right? Good. Okay? So it's basically any x that such that it's not equal to pi over 2 or any multiple of pi over 2, right? It can't be pi over 2. It can't be 3 pi over 2. It can't be 5 pi over 2. It can't be negative pi over 2. It can't be negative 3 pi over 2 or negative 5 pi over 2. So it can't be any multiple of pi over 2. So that's the easiest way to say it. Okay? Every pi, we have another asymptote. So we can't be pi over 2 or any pi increment of that. So that's where we put the n in there, where n is an integer. Okay? Range. All real numbers. Unlike sine and cosine, which only had a range of 1 and -1, -1 to 1, this one can actually be all real numbers. Okay, where are the vertical asymptotes of this parent function tangent? Pi over 2, 3 pi over 2, etc., right? So pi over 2 plus any pi multiple of pi over 2. Bless you. Bless you. And because it's an odd function, it's symmetric with respect to the origin. Okay? All right, so what is going to happen here? We just learned about this guy, and now you're messing with it. Yes. Okay. So what's happening with this guy? That 2, the first 2 is going to stretch it, so it's going to get higher even faster. Okay, at 45 it's not going to be at 1, it's going to be at 2. Okay, so it's going to be stretched and elongated. It's going to make its move a lot quicker. And the other one tells me how often we have a period, right? Before it was every pi. Now we're going to get a new one every pi over 2. Okay? Why would they do such a thing to us, right? Okay? So it's going to be stretched. We're not shifting horizontally or vertically. Okay? Before our asymptote was at pi over 2, wasn't it? Now it's going to be at pi over 4. Okay? So now it's going to do its thing, and it's going to do it faster. It is at pi over 4 because of this 2, correct? That changed the period. Anything that's multiplied by x changes the period. Exactly. Instead of having an asymptote at pi over 2, now we have an asymptote at pi over 4 and another one at negative pi over 4. So it's just happening twice as fast as if it wasn't busy enough already. And instead of 1 pi being a complete period for it, now it is 1 pi over that 2, so pi over 2. We get a full cycle. Yep, I just drew some vertical asymptotes. So I'm going to do another one right here. And remember, those asymptotes are not part of your graph. Okay? And so this guy's going to go through here. And you could go crazy with that. No. You don't have to do them all. So I can see that you know what you're doing. Okay? All right, everybody good on this one? Quiz over this is on Monday, over graphing. The 2 before the tangent is going to be a vertical stretch. Okay? So it's making it taller faster. At 45, instead of being up at 1, it's going to be up at 2. Okay? All right, here we go. Introduce you to cotangent. Okay? All right, so let's think about cotangent. Cotangent is the reciprocal of tangent, isn't it? Okay? Okay. I believe you. Okay, so cotangent. The cotangent is basically the tangent just 90 degrees removed, just like the sine was, right? Okay, so that's another way of thinking about it. Or it's the reciprocal of the tangent. So when we were at 30 degrees, the tangent was square root of 3 over 3. That means the cotangent is just plain old square root of 3. At 45, the tangent was 1. The cotangent will also be 1. And at 60, the cotangent was the square root of 3, so it's going to be the square root of 3 over 3. Okay? At 0, the tangent was 0, and at the cotangent is going to be undefined. And at 90, when the tangent was undefined, the cotangent will be 0. Okay? So now let's look at what this guy is going to appear to do. So at 0, we're undefined. There's our vertical asymptote. Okay? At 30, we're the square root of 3. That was that what? 1.7 or whatever? Because the cotangent is the reciprocal of tangent, so it's undefined. So this is 1.7, okay? So we're at 1.7 when we're over here at 30 degrees, okay? Almost at 2. And then at 45, we're coming down, we're at 1. And at 60, we're at that 0.57, aren't we? 0.6. And then at 90, we're at 0. Okay, what do you think it's going to do as we continue on? Keep going down, won't it? Okay, until it gets to pi but can't reach pi, can it? Okay, so tangent did the John Travolta to the upward to the right. The cotangent is doing the opposite. Yep, absolutely. The tangent and the cotangent are going to switch asymptotes. Okay, because what was okay at 0 degrees for tangent is not going to be okay for cotangent. We can't divide by 0. Okay. So let's do another iteration of that, and then you're good with cotangent. So we're okay at negative pi over 2, but we're not okay up here. So quick sketch. Not looking for accuracy and precision here. Okay. All right. Next one. Introduce you to another new friend. Cosecant. Okay. Hello, cosecant. How are you? Okay. Well, cosecant's kind of not happy because it's always the reciprocal of something, right? It doesn't get top billing. It's not the lead actress or actor. Exactly. This is 1 over the sine. Okay. So where are we going to have problems with 1 over the sine? Let's think about it. I'm going to graph the sine here really quickly. Hopefully you haven't forgotten how to do that. Zero, zero. Yep. Sine, you start at the origin. There's my sine. Okay? That's the sine. Okay? Sine of x. Okay? Now let's think about what the cosecant is going to do. I love the cosecant. It's fun. Easy to graph. It is. Yeah. Yep. And it's going to go a little crazy here. Okay? Because it can't be 0, can it? Okay? Can we be 0 for cosecant? No. So we need an asymptote. And we can't be pi. We need another asymptote. And we can't be 2 pi. Another asymptote. Because what happens when we're at 0? And the sine of 0 was 0, but if we flip that 1 over, we're going to be undefined, aren't we? So we can't be pi, negative pi. And we can't be negative 2 pi. It's up to you if you need them to as a guide. Okay? Now let's think about what happens at pi over 2. The sine of pi over 2 is 1. So what's the cosecant of pi over 2 going to be? 1. Okay? So at 1, we're 1. Okay? Let me do this in a different color. Okay? What about at 3 pi over 2? Negative 1. At negative pi over 2? Negative 1. And at negative 3 pi over 2? Positive 1. Okay? So that's where they're the same. Okay? It's coming together. Okay? Here's the crazy part. At 30 degrees, what was the sine of 30? Sine of 30 was 0.5 or 1/2, right? Not tangent. I'm thinking tangent. What was the sine of 30? 1/2. Flip it. 2. Cosine of 30 is 2. Okay? And cosine of 120 will also be 2. Can you see what it's going to do here? It's going to be like a parabola, isn't it? Lots of little parabolas going on. So cosecant and secant are my favorite ones to graph once I know what sine and cosine look like. Because they're fun. They're easy to sketch them. But you've got to have the sine and cosine down. Okay, looks pretty. Okay, everybody good with cosecant? What's the secant going to look like? Absolutely, it's going to be shifted 90 degrees, isn't it? The same thing as the cosecant was, but shifted 90 degrees. So always start these with your sine or cosine. This one is the reciprocal of cosine. So start with your cosine, and cosine starts at 0, it's at 1. Asymptotes then, any place that the cosine is 0 is going to be an asymptote for the secant. Okay, so here was my normal cosine. Okay, draw your asymptotes. Anywhere there's a 0, we can't touch this. Got the MC hammer down. And now draw your secant. And again, your calculator, if you don't have it set properly, will draw those asymptotes as part of the graph. They are not part of the graph. And now we have the secant. Okay, thank you. All good? Okay. All right. Now this is evil. Now that we've introduced you to secant, we're going to make you slide them over. Okay? Okay? Okay. Oh, okay. Okay. Focus assignment on the blog. Okay. All right. So secant of x plus pi. But it doesn't have to be evil. Okay? Secant is 1 over what? 1 over cosine, right? Okay? So do we know how to graph the cosine of x plus pi? Sure. We're going to shift it which way? To the left pi. Okay? So we're moving it to the left pi. The cosine is normally starting at 1, right? So it's still going to be starting at 1, but it's to the left pi. Bless you. Okay? Okay? Then it does this. So the key to graphing secant and cosecant is to graph the sine or cosine, the cosine and the sine, respectively. Okay? Okay? Now put your asymptotes in. Does that look like anyone we just graphed? This kind of looks like the cosecant, doesn't it? Okay? Does that make sense that it would be? Okay? So we shifted this guy by saying I'm going to shift my cosine so I know where my pattern is going to go. And I'm shifting the cosine 90 degrees to the left. Pi to the left, because it's plus. So I moved it. Normally, cosine would have been here, right? But I had to move it pi to the left. So now that's been translated. Okay? X plus pi, did I do this wrong? X plus pi, we're moving it 90 degrees to the left. So we would normally start high and go down. Yep. Okay? All right. Last one. I want to introduce this to you. I promise you won't have to do one this complex on your test, but I want you to practice it. Yep, left, pi over 3, 60 degrees to the left. Stretch negative 3. So this is going to be a lot steeper, but reflect. Okay. And this graph paper is not good for this. Okay. So if it's better to not have the graph paper and create your own, because I didn't give you a left pi over 3. Okay. You can certainly put a left pi over 3. Now cosecant is 1 over the sine. Okay. So we want to go pi over 3 to the left. Okay. And we're going to do 1 full period. Okay. So what would be 2 pi short, or pi over 3 short of 2 pi? That's 2 pi minus pi over 3. 5 pi over 3. So we're going to end up at 5 pi over 3. Okay? That's going to be one full period. Okay? This is negative pi over 3. We're shifting it left pi over 3. Okay? So my 2 pi would be over here somewhere. We're just going to show one full period, and we're good. Oh, thank you. Cosecant is every pi. You're right. So what's one full one? Okay, so 2 pi over 5 pi over 3 minus a pi, 2 pi over 3. Okay, so if we want one full period now, we would say sine usually starts at 0, right? And then it would have to go down 3. Okay, this was negative 3 and this was positive 3. Yep. Running out of time. Okay. Assignments on the blog. Thank you.